Hello, my name is Darren Thomas and I am the Director of Educational Research Techniques, and this is Simpler Using Machine Learning Algorithms in R. We're now in Unit 9, Chapter 9, and we're in Lesson 3. And we're going to take a closer look at the confusion matrix output. In particular, we're going to use a function inside the caret package that's going to give us deeper insights. And so what's going to happen is that I'm going to run the initial output, and then I'm going to show you some slides that kind of explain what the different metrics mean. And after we do that, we're going to compare our linear discriminant analysis model with our quadratic discriminant analysis model to see which one is better at predicting gender based on the other variables available in the wages 1 data set. So without wasting any more time, let's go over to R. And so here I am, I'm inside R, and the packages we need are at the top here. Most of this is already familiar with you. The caret package might be new. This might not have been in the prior code. So we press Control Enter. And now what we're going to do here is we're simply going to do our model comparison. And so right here in line 3, we have our predict model. We made this previously when we did a linear discriminant analysis for in the previous video. And we were trying to predict class based on, we're trying to predict someone's sex based on, the other variables in the wages 1 data set. And so now that we've already completed that, we're going to look at the confusion matrix, but this is actually the name of a function inside the caret package, and it gives you a lot of output. So I'm just going to go ahead and run line 3, press Control Enter. I'm sorry, let me go right here. Control Enter, there we go. And here's all our information. Let me make this a little bit bigger for you. Okay, so you can see here it gives you a lot of information. So we first here have the regular confusion matrix. We've seen this before. The number of true positives, true negatives. I believe right here is false positives, and down here are the false negatives. Okay, so the first thing they give is the accuracy, which is 62%. Not that amazing, but it is what it is. Then they give you the confidence rating. The information rate is something else that can be valuable, and the p-value, which is significant for the information rate. The kappa, let me go ahead and show you what these mean here in the inside our slide here. So accuracy, you guys know what that is. Here's how you calculate it, like so. True positives. I'm sorry, the TP stands for true positive. I just use a shorthand here. Now the kappa, which is what we just left off on. And let me see if I can make this a little bit bigger for you, is the accuracy of a model while taking into account chance. So the kappa tells you how good the model is when you also are trying to adjust for random success through guessing. And so the higher, the closer the value is to 1, the better. So if we go back here, you see our kappa is 0.24, very, very poor. So this model is not that great. But again, this is just a different metric for adjusting for accuracy. Mick tomorrow's test of p-value, we'll deal with that at a different time, maybe not now. Now, sensitivity and specificity, let's take a look at those. So sensitivity is the proportion of true positives that were correctly classified. And so here is how you solve for that. You take the true positive divided by the true positive plus the false negatives. And that gives you an idea of sensitivity. Now, different times, you're more worried about false negatives or false positives. Let me see if I can give you an example. Let's say you're a doctor and you're doing medical testing, for people who might have cancer. A false negative will be much more disastrous than a false positive, because if someone receives a false negative, you are telling them, hey, you don't have cancer, when they actually do have cancer. That could have catastrophic consequences, life or death. Whereas if someone gets a false positive and you tell them they do have cancer when they do not, yes, they go through expensive treatment, and yes, they waste a lot of money, but in many ways, it's better to waste the money on the treatment that you don't need than to not get treatment that you do need. So these different metrics serve different purposes depending on what the ultimate goal of your model is. And so with sensitivity, it tells you the proportion of true positives that were correctly classified. In other words, the proportion of people who have cancer who were correctly classified as having cancer if we were to extend my medical example that I just used a few moments ago. So that's what that does. Now next we have specificity. this is the measure of the true negatives that were correctly classified. So you don't have cancer and you really don't have cancer. That's what specificity measures. And so again, these are both on the scale of up to 1. So you can see for sensitivity, we got 0.58. Specificity, you got 0.65. It is what it is. And going back here, we have also precision and recall. Precision is the proportion of examples that are really positive. So true positive divided by the true positive plus false positive, and recall is a measure of the completeness of the results of the model. True positives plus true positive divided by true positive plus false negatives, which is the same as sensitivity. So recall and sensitivity are different names, but they use the same measuring tools, but again, they serve different purposes. So you can see here that we don't have precision and recall available here, but these are other tools that you can use if you are trying to do an analysis. But the main ones here are sensitivity and specificity. Excuse me. Now, the F measure, which is also not available here, uses recall and precision to develop another metric. So down here at the bottom is 2 times the true positive divided by 2 times the true positive plus the false positive plus the false negative. And so again, that's another metric that you can calculate. Some functions calculate it, some functions do not. But in our purposes, this is what we have right here, is these metrics that are available. So that gives you an idea. You understand what kappa is, you understand what sensitivities and specificity is, you understand what F1 measure, precision, and recall are, and of course accuracy, the most common metric. Now, this is what we're going to do. These are the results right here for the LDA model. And so again, one reason we do all these metrics is that we want to use them for the purpose of being able to compare models. So what we're going to do now is that we're going to compare the results we have here with the results we get with our QDA model. So what I'm doing now is I have 2 R sessions open here. To the left, I have the results for the linear discriminant analysis, and now to the right, I'm going to run the results for the quadratic discriminant analysis model. So we go ahead and run this. Okay, so now they're right next to each other. Let me go ahead and close this so you can see everything as much as possible. And so you can see here, if we just go right across, accuracy is about the same, 0.62, 0.61 basically. The kappas are about the same, 0.24, 0.21. The sensitivity is much better on the quadratic discriminant analysis. Again, going back to our other screen here, sensitivity was the proportion of true positives that were correctly classified. So people who have cancer and who are to really have cancer. So if we were worried about true positive rate, we can make the choice that, hey, it might be better to go with the quadratic discriminant analysis model. However, specificity is 0.65 for the linear model, but 0.49 for the quadratic model. So if we're more worried about negatives, correctly dealing with true negatives, it might be better to go with the linear discriminant analysis model. So you can see here the rest of the metrics are surprisingly similar. What we're trying to do here is we're trying to show you that how to determine your model selection must be based not just on raw numbers like accuracy, but on the overall purpose of your model. And so again, in different situations, the quadratic or linear model in this context will be more useful than the other. Something else that needs to be mentioned as well is that you cannot improve all the metrics at the same time. For example, you might adjust the model, tune the model to increase sensitivity, or by doing so, you might lose some specificity, excuse me, or you might lose something else, or you might want to tune the model to move the specificity. This is hilarious. Specificity, but then you might lose some sensitivity, or you might lose some accuracy. So there's always a give and take and a trade-off when trying to develop models and trying to deal with these conundrums, these challenges that we face as we develop these machine learning, as we work with these algorithms. So what happened in this video is that we learned a great deal about how to assess confusion matrices and how to deal with them. And so there is a function in the caret package called confusion matrix. It's right here in line 3. And this will give you some printout for a lot of useful metrics that you can use. And of course, you can take the information inside your actual confusion matrix table here, and you can calculate all of the other ones. And of course, there are other functions that are available that will give you the F1 score and the other things like that, etc. But again, when you are trying to decide on how to deal with your models, you have to keep in mind what is the ultimate purpose of your model and to do things accordingly. So, my name is Darren Thomas. I'm the Director of Educational Research Techniques. This is Simpler Using Machine Learning Algorithms in R. Take care.